Chapter 4.4, Indeterminate Forms and LHopital's rule. Now for this section, we are actually going back to limits. We are looking at limits again and taking a look at the behavior of this entire function as x approaches 1. Now taking a look here at these two functions, the function in red, the natural log of x, and the function in blue, x minus 1. Now if you take a look, as x approaches 1 for the natural log of x, the output gets closer and closer to 0. So this value actually approaches 0. If I call this f of x, the limit of f of x as x approaches 1 becomes 0. And if I take a look at this blue model right here, as x gets really closer and closer to 1, my output also becomes 0. As x approaches 1, my g of x also becomes 0. Now how telling is that? First of all, I can't just drop in the number 1 here because then I get a does not exist, right? So does 0 divided by 0, if I get 0 divided by 0, does the limit exist? Is the limit existing right now? Is it equal to 0? Or is it 1? Does 0 divided by 0 equal to 1? Is it neither? This is what we call an indeterminate form. Now, taking a look at example 2, and we'll come back to that, but taking a look at example 2, here's another one. As x approaches 0, the output of the green function becomes closer and closer to 0. So if I call this f of x, and I call this g of x, the limit as x approaches 1 of this f of x, and the limit as x approaches 1 of this g of x is also what we consider indeterminate. Because 0, I get 1 minus 1 on top is 0, 1 minus 1 on bottom is 0. Now how does that division actually compare? Right? Does it equal 0? Does it equal 1? Does it equal does not exist? Well, in this case, try factoring. We actually know how to solve this. So let's try factoring here. The limit as x approaches 1, if I factor out x, I get x minus 1. On the bottom, I can factor out x minus 1, x plus 1. These cancel. If I drop in 1, now I don't have a domain issue. This limit, even though the limit of the top and the bottom goes to 0 and 0, the actual limit itself, the division of it, gets closer and closer to 1/2. Okay, so how do I determine the limit for functions like this? Well, moving on to the next example. We'll come back to that. Now, the limit as x approaches infinity is another one, where as x approaches infinity in the top, if I call this f of x and I call this g of x, the limit of f of x as x approaches infinity over the limit as x approaches infinity of g of x. If I take the limits separately, and as x gets really, really big, this red function here goes up to positive infinity. The blue function on the bottom also goes up to positive infinity. So does positive infinity divided by positive infinity equal to 1? Does it not exist? Does it go up to positive infinity? Well, if you take a look, it does have something to do with the slope. Is this increasing? Is the red value, the function on top, increasing significantly faster than this bottom function, where the division, where the quotient of it will equal to just continue to increase exponentially? Well, that is where LHopital's rule comes into play. Now, for indeterminate forms, the two that we've gone over in example 1 and example 1, 2, and 3 is when we take the limit as x approaches a value, we get 0 over 0, or we get infinity over infinity. And this is, again, only for limits. So this is for limits only. Only when we are talking about limits do we have indeterminate forms. Now, if the limit of f of x reaches 0 over 0, or infinity over infinity. Those are the two that we've gone over right now. Or if it yields a product of 0 times infinity, or a difference of infinity minus infinity. These are all things that you cannot tell whether the limits actually exist. You also have powers, where if you have 0 to the 0 power, or infinity to the 0 power, or 1 to the infinite power. These are also indeterminate forms. Now the main one is here. When you have a quotient that's 0 over 0 or infinity over infinity, we can apply L'Hopital's rule. So these limits may or may not exist. One method to find these limits is by using L'Hopital's rule. Now L'Hopital's rule takes into consideration the limit as x approaches a value of f of x over g of x. Okay. Now, if I take the limit of each of those separately, the limit as x approaches a of f of x and get 0, and I take the limit as x approaches a of g of x and I get 0, or if I take the limit of the top and bottom separately and I get infinity over infinity. These two are my two indeterminate rules of a quotient. Then L'Hopital's rule tells me I can actually take the limit, find the limit of this quotient by taking the derivative of the top and the bottom separately. So this is not the product rule. We are actually taking the derivative of the top function and the derivative of the bottom function completely separately, and we're analyzing the comparison of the ratio of their slopes. So going back to example 1, in this example right here, L'Hopital's rule tells me if I plug in 1, natural log of 1 becomes 0. 1 minus 1 becomes 0. So this is an indeterminate form of 0 over 0. So I can actually apply L'Hopital's rule, take the derivative, sorry, I'm still looking for the limit, take the derivative of the top function divided by the derivative of the bottom function. Now, all I'm doing is taking a comparison of the ratio of their slope functions. Now, as x approaches 1, now I can just drop that in. So 1 over 1 is just 1. So the limit of this particular indeterminate form is 1. Going to the bottom, example 2. I am now taking the limit of as x approaches 1. We've tried this by factoring. Now let's try it by using L'Hopital's rule. Now L'Hopital's rule can only apply to indeterminate forms. So when I plug in 1, 1 minus 1 is 0. Plug in 1 here, 1 minus 1 is also 0. So I have to check to see that I have an indeterminate form. Now again, if I'm applying L'Hopital's rule, I'm finding the derivative of the top and the bottom entirely separately. And I'm taking a ratio of their slope functions. So I'm taking the derivative of x squared minus x, taking just the derivative of the top, and I get 2x minus 1 all over 2x. Now, can I drop in 1 yet? So it looks like at this point I can. So I'm not taking this as x approaches infinity, don't forget. So the ratio here is not 1. Can I plug in 1? I can. So 2 times 1 is 1 minus 1 is 1. Sorry, 2 times 1 is 2. 2 times 1 here is 2. So this ratio, even though the limit of these separately was 0 over 0, the limit of the entire function together as a quotient is 1/2. Moving on to example 3. As x approaches infinity, what do I have? Well, as x gets really, really big, e to the x approaches infinity. As x approaches infinity here, x squared approaches infinity. So we have another indeterminate form. I can apply L'Hopital's rule, find the derivative of the top and bottom. I get e to the x over 2x. Right? So again, no quotient rule here. I'm just finding the derivative of the top separate from the derivative of the bottom. And I get e to the x. I can apply Well, in this case, as x gets really big here, x approaches infinity. As x gets really big here, 2x approaches infinity. I have another indeterminate form. I can apply L'Hopital's rule again and get e to the x over 2. Now in this case, this is enough to say this is a constant of 1/2. As x gets really big of e to the x, this quotient, the limit as x approaches infinity, e to the x grows infinitely bigger than x squared, so the limit is infinity, positive infinity. So this last example that we're going to do on this video is a warning example to not get too L'Hopital happy. Now what do I mean? Let's say you're in the L'Hopital section and you know it's about L'Hopital's rule. So you see a limit like this. As x approaches pi from the left side, sine x over 1 minus cosine x. And you immediately jump to taking the derivative of the top, which is cosine x, over the derivative of the bottom, which is negative sine x times a negative, so it's positive sine x. Now, as x approaches pi from the left-hand side, this cosine of pi becomes negative 1. Sine of pi from the left-hand side becomes, well, 0, but it's actually a really small, so let's take a look. Sine of pi from the negative side is a really small fraction, right? So this one will actually approach positive infinity because the number on bottom will become 1 over some really tiny fraction, right? So this will take the reciprocal, it'll approach positive infinity. Okay? This in actuality is wrong. We jumped from here, we jumped to L'Hopital's rule way too quickly. Because what did we forget to do? We forgot to check to see if this was actually an indeterminate form. What is the sine of pi from the left-hand side? Well, this approaches 0. 1 minus cosine of pi is actually negative 1. So this actually becomes 1 minus negative 1, which is 2. So what is this limit? So this was all wrong. This was not an indeterminate form. Which means taking the derivative of the top, applying L'Hopital's rule was wrong from the start. Here, I can actually just plug in pi into the denominator. I don't have a domain issue, so I actually get 0 over 1 minus negative 1, which is 2. So this limit actually becomes 0 over 2, which is 0. So that's my last example for today. In class, we will be going over, so let's going back to all our indeterminate forms. Wrong one. This one. Going back to our indeterminate forms, this is where we apply L'Hopital's rule to. So this is for L'Hopital's rule. For each of these forms, whenever you have a product or a difference or a power that is indeterminate, we must change all of these to a 0 over 0 or infinity over infinity. And those examples, which take a little bit longer, we will be going over in class.